Hi, this is Kranti. I have done my research project on empowering energy management, predictive modeling for user-centric electricity consumption forecasting. In introduction, I'm gonna say background behind this motivation, uh, research objective, and impacts. When it comes to background, in recent years, global attention has increasingly focused on sustainability and energy efficiency. Driven by environmental concerns and regulatory pressures, the management of electricity consumption plays a pivotal role in achieving these goals, necessitating innovation approaches to optimize energy users. Motivation uh, behind these research teams from the evolving landscapes of energy grids, which are becoming more intricate and interconnected. There is a corresponding increase in the demand for more efficient utilization of energy resources to meet growing global energy needs sustainably. The primary objective of this study is to leverage advanced machine learning technique to develop accurate predictive models for forecasting electricity consumption. By enhancing forecasting precisions, we aim to empower utilities and consumers alike to make informed decisions, thereby improving overall energy management strategies. There are benefits by this, like optimization of energy usage, which enables utilities to efficiently distribute and allocate energy resources based on the predicted demand. When it comes to cost reduction, helps for the consumers uh, to make the plan the budget, reducing operational cost. Environmental mitigation facilitates the reduction of carbon footprints by optimizing energy consumption patterns and integrating renewable energy sources more effectively. Uh, why energy consumption forecasting matters? The challenge of unpredictable electricity demands impacts both operational efficiency and cost efficiency in energy management. Accurate forecasting enables better planning, reduce unnecessary energy consumption, and supports grid stability. In cooperation, user-centric behaves uh, and needs into forecasting models can significantly improve prediction accuracy and user satisfaction. Challenges in current energy management system, traditional forecasting models often fail to account for more variability and complexity for user-driven electricity consumption patterns. The lack of integration between the user-centric data and the predictive models leads to insufficiency in energy distribution and management. This research addresses these gaps by developing models that integrates user behavior into predictive frameworks, aiming to improve both accuracy and applicability in real-world scenarios. In terms of business, the primary problem we address in this study is the need for reliable energy electricity consumption forecasting. Accurate forecasts are essential for energy providers, local government, consumers, and environmental agencies. The key stakeholder includes energy providers who need accurate forecast for effective energy management, local governments that use the forecast for infrastructure planning and policy makings, while consumers who benefits from insights to reduce their energy cost, environment agencies that leverage forecasts to promote sustainability. The main goals are to optimize energy usage, reduce operational cost, and improve the efficiency of energy management and planning. Let's take a overview of methodology. This research study involves several critical stages. Develop accurate predictive models for electricity consumption forecasting. Here you can see the different stages. First, the data collection, data processing, model selection, training and validation, evolution, and the final model. In evaluation, for the predictive model, we'll focus on three key matrices like root mean square error, mean absolute error, R square score. RMSE measures the average magnitude of prediction errors, providing insight into how well the model cap- captures variability in electricity consumption. MAE reflects the average applied difference between predicted and actual values, offering a straightforward interpretation of the model's accuracy. R square score matrix represents the uh, proportion of variances in the target variable explained by the model. A higher R square score indicates better model performance, significating the model's ability to make accurate predictions. These matrices collectively helps assess the accuracy, reliability, and generational and capability of the predictive models. Uh, Dataset collection. I have taken dataset from Kaggle, which consists the detailed hourly electricity consumption records of Alabama drought USA. It includes essential features such as date, time, energy consumption values, providing a rich temporal context crucial for capturing consumption patterns. This granular level of data allows us to analyze and model daily and seasonal variations in electricity consumption accurately. Understanding these patterns is essential for developing robust predictive models that can adapt to changing environmental and socio-economic factors. Here is the representation of electricity consumption of interior versus the exterior lights. Major portion is used by the interior lights, and there is a short portion which implements exterior lights. Here in the next graph, we can see the electricity fluctuations of a whole day, where highest electricity is consumed at 8 a.m. to 9 a.m. of 10 kilowatts, and the lowest at 4 p.m., which is 2.5 kilowatts. Data preprocessing, handling missing values on outliers. Missing values are implemented using methods like forward filling or mean implementation to maintain datasets completeness. Outliers are defectors and addressed to prevent bias in the model performance. Pre-processing, data cleaning involve handling missing values, normalizing energy consumption matrices, and converting date format time. Here, I had first done removed leading and trail spaces from the date time column, then replaced the 24-hour time format into 00 and adjust the date accordingly. The data set was categorized into three types: high, base, low level energies for more granular analysis. Then all these the three data sets are combined together to get a single comprehensive data frame, providing a unified view of energy consumption across different scenarios. Model selection. I have done my model selection two parts. In first part, random forecast and gradient boosting. Random forecast is an assemble learning method that operates by constructing multiple decision trees during training and outputting the mean prediction of the individual trees. Handles large data sets well, reduce overfitting, and is effective in capturing complex data interiors are the advantages. When it comes to gradient boosting, is another assemble technique that builds models sequentially, where each new model attempts to convert the error of the previous ones. Known for its high accuracy, especially in unbalanced datasets, and is uh, liability to handle various types of data. In part 2, long short-term memory and gated recurrent units are used. LSTM is a type of recurrent neural network capable of learning long-term dependence crucial for time series forecasting advantages. Retain important information over a long period, handles complex temporal patterns, and is highly effective in sequential data analysis. GRU is similar to LSTM but with a simplified architecture which makes it faster and more efficient while still capturing dependencies in sequential data. The advantage, it combines the strength of RNNs and LSTMs, offering a balanced between complexity and performance, particularly effective in processing time series data. Hybrid model development. Uh, Developed a hybrid model by avenging the prediction from random forecast, gradient boosting, LSTM, and GRU models. The, the approach aims to combine the strengths of each model, reducing the impacts of the individual weakness and improving overall prediction accuracy. When it comes to individual model structures, we can learn some issues at the end, but when in the hybrid model structure, when it combines two different outputs and corrects the issues and gives us a correct output without any mistakes. Expected outcomes. Hybrid model is expected to deliver more reliable and accurate forecast by leveraging derived prediction strategy, particularly in case of complex co- consumption patterns. Model training. Random forecast and gradient boosting models were trained using the preprocessed data set with hyperparameters turned into optimized performance. In training process of this, we used a cross validation to ensure that the models generalize well to unseen data. Hyperparameters such as the number of trees in the random forecast forest and the learning rates in gradient boosting were optimized. In LSTM, GRU models were trained on time series data with training loose visualized over multiple opposed to monitorized performance, while training LSTM and GRU models were trained for 50 epochs with batch size of 32 using an Adam optimizer and mean square error loss function. Visualization of the training process showed consistent learning with loss susceptibility decrease over time. Model prediction. When you random forecast and gradient boosting, both models produce accurate prediction with random forecast slightly outperforming gradient boosting in terms of RMSE and R square. Uh, I have observed random forecast predictions were close to the actual values, particularly in scenarios with high validation. Gradient boosting showed slightly higher variance, particularly in the tail ends of the distribution. LSTM and GRU, this have a deep learning models providing highly accurate prediction, particularly efficiency in capturing complex temporary dependence. I have observed LSTM and GRU closely match actual consumption values, with GRU slightly outperforming LSTM in terms of accuracy, but both models demonstrate strong capability in handling the sequential nature of the data. Model When it comes to model evolution, random forecast provides solid performance but slightly less accurate than deep learning method. Gradient boosting a higher variance in predictions compared to random forecast, particularly in high consumption periods. LSTM slightly outperform GRU, making it the best model in this evolution. GRU delivers excellent accuracy, especially in capturing temporary patterns. Here you can see the different outcomes of them. Hybrid model performance. As I said, I have used three matrices RMSE, MAE, R square. These are the values 0.0211, 0.0138, and 0.99998. I have obtained them. Performance analyzing. The hybrid model successfully combines the strength of all models, achieving a balanced and highly accurate prediction outcomes and resulting in the superior model in the R square score to the number 0.999792. The hybrid model demonstrates its effectiveness as a practical solution for energy consumption forecasting, practically in scenarios where accurate and reliability are paramount. Uh, my key findings and insights in this hybrid model emerged as the top performer as the model evolution by combining the advantage of all individual models, followed by the indivi- individual model LSTM, GRU, random forest, and gradient boosting. The LSTM and GRU models provide the best overall performance other than from all individual models. Practical implementation, these models can significantly enhance the accuracy of energy consumption forecast, leading to better energy management strategies. In cooperation, user-centric data is predictive model shows great potential in tailoring energy management to specific user needs. Further research could explore indicates real-time data and external forces like weather or economy. Weather indicates a future improve forecasting accuracy. In conclusion, this research highlights the importance of advanced predictive modeling in energy management, showcasing the potential of hybrid model in improving forecasting accuracy. The study findings contribute to the development of more efficient and user-centric energy management system with significant implementation for both utility companies and consumers. In future work could focus on incorporating real-time data streams for dynamic forecasting and decision making. Investigation the impact of external factors like weather condition, economic trades, and policy changes on energy consumption could enhance model robustness. Uh, Border applications. Applying these models to other datasets or domains such as renewable energy sources or smart grid management could provide future insights into their versatility and effectiveness. Call of action encourage ongoing exploration and innovation in the field of predictive modeling for energy management, emphasizing the need for continued collaborating between academic and industries to drive advancement in the critical areas. Thank you for giving this opportunity.